Hello everyone, today we are covering a topic from IGCSE Cambridge Chemistry, lesson Organic Chemistry, topic Polymers. Polymers are large molecules that are made up of small units called monomers. Poly means a lot. So polymer means a lot of monomers. A lot of monomers linked together forms a polymer. Now, each of these polymers are made out of either repetition of one monomer or the repetition of several monomers. Because of this, different polymers have different units and linkages. Different type of monomers can have different functional groups attached to them. And depending on the functional group, the number of carbons in the monomer, the way the monomers link to each other also differ. And because of that, there are so many types of polymers that can be formed. Polymers can be linked with carbon-carbon linkages, ester linkages, or amide linkages. And we'll be talking about all three types in this lesson. There are two main types of polymers, synthetic polymers and natural polymers. Synthetic polymers are man-made polymers, whereas natural polymers are the ones we can find in nature. So let's look at a few examples for natural polymers and synthetic polymers. Some of the natural polymers are protein. Protein can be found in our hair, skin, and tissues. And there are polysaccharides. Polysaccharides are cellulose and starch. And there's also polynucleotides. DNA and RNA are examples for polynucleotides. And then let's look at the synthetic polymers. These are the man-made polymers. So there's nylons, polyesters, acrylic, polyvinyl. These are the plastic sheets, the plumbing material, pipes that we use are all polyvinyls. And there's also polystyrene. Polystyrene is used as thermal insulating material. There are two different ways that we can use to make polymers: addition polymerization or condensation polymerization. First, let's look at additional polymerization. Addition polymerization is the way that you use to make polyethylene or polyethylene. Now, addition polymerization can happen when there are alkenes as monomers. And in addition polymerization, the linkages between each monomer that makes up the polymer is a carbon-carbon bond. So in this example, we are going to look at the formation of polyethylene. Here we use the alkene ethene to make polyethylene by using addition polymerization. So here, first, in any type of polymerization, first you need to identify the monomer, then the repeating unit, and then what the polymer looks like. The monomer here is the ethene. So ethene has two carbons. Each carbon has two hydrogens each and a double bond with between the carbons. In polymerization and addition polymerization, what happens is this double bond breaks and it branches out, reaching out to another atom that looks like another molecule that looks like this. When several of these monomers branch out like this, they add together. So more molecules like this, they come and join each other. So your repeating unit of the polyethylene would look like this. It is a branched out ethene. The double bond had been broken. Now there's a single bond and two bonds reaching out to another molecule. And the polyethylene would look like this. It's going to go on forever from the left hand side to the right hand side. Polyethylene can have different carbon chains. different length carbon chains. So a lot of such repeating units will keep on repeating and repeating to make the polyethylene. If it's too troublesome to draw a lot of carbons like this, you can also draw the polythene with the repeating unit and an N like this. This N represents that the repeating unit is repeating N number of times. That is also good enough if you are asked to draw the polythene. If you are asked to draw the repeating unit, just the repeating unit, then you have to draw it without the N, like this. And if you are asked to draw the monomer, then you can't have these branches out. You have to have the ethene with the double bond. Now let's look at condensation polymerization. Now, it is condensation polymerization that results in a ester linkage or an amide linkage. First, let's look at the formation of polyester. Here you will see an ester linkage. Now, one type of polyesters is called herilene. Herilene is made up by condensation polymerization. So, the first products or the monomer, the first thing we need here, the monomer we need is a dicarboxylic acid and a dialcohol. So for condensation polymerization, unlike addition polymerization, we always need two molecules. For addition, it's only one molecule that is been repeating. But for condensation, we need two. And the two has to have the same functional group at both the ends of the organic compound. See, it's a dicarboxylic acid and a dialcohol. It means there's a carboxylic acid at the left-hand corner and right-hand corner. Dialcohol means there's a OH group at the left-hand corner and the right-hand corner. And just so that you don't get confused, this box represents whatever the number of carbons in between the two functional groups. It could be CH2, it could be C2H4, it could be any number of carbon chain that is in between this box. We just draw a box so that we don't have to repeatedly draw a long carbon chain. Okay? And to make sure we identify these two atoms separately, when we are actually drawing the polyester, we can draw two different boxes, one colored like this and one not colored. That's what you can see in this example. So in the condensation polymerization, what happens is the reaction that happens here is very much like esterification. The OH of the carboxylic acid, it goes away with one H of the hydroxyl group here and becomes H2O. The remaining part of the carboxylic functional group attaches to the oxygen of the hydroxyl group of the alcohol. And it makes this ester bond or ester linkage. Just like that, at both ends, ester linkages happen, combining a lot of such monomers. So it will always be dicarboxylic dialcohol, dicarboxylic dialcohol, and one after the other, they would line up to make a polyester. So if they ask you to draw the monomer, you need to draw these two monomers, dicarboxylic and dialcohol. If they ask you to draw the repeating unit, then you need to draw one with the ester linkage. Remember, when you're drawing the repeating unit, you don't write the N. And then if they ask you to draw the polyester itself, then you can put the N. Or you can also draw several of the monomers linking like this. See here, this colored box represents the dicarboxylic acid, and the non-colored box represents the carbons and hydrogens in the middle of the dialcohol. Don't get that confused. That's why we have these boxes in between. And just like any other condensation reaction, there will be a water molecule lost during this reaction as well. Now let's look at the condensation polymerization of a polyamide. Here you would see an amide linkage. An example for a polyamide is nylon. Polyamides also undergo condensation polymerization. So here we need an amine and a carboxylic acid functional. It's not just any amine or carboxylic acid. We need a diamine and dicarboxylic acid. For example, the carboxylic acid should look like this. Now this box, like I said before, represents the amount, the number of carbons and hydrogens in between any length. So we need a dicarboxylic acid as such and a diamine. These are going to be the monomers of our polymer. Okay, so we have a diamine. This is a diamine, and this is a dicarboxylate. So these two monomers will get together to make this polymer by undergoing condensation polymerization. Here also, the OH of the carboxylic acid will go out with one of the hydrogens of the amine to form a water molecule. The remaining carbon that now needs a bond will bond with the nitrogen to make this kind of an amide bond. Amide bond you can see here. A bond between a nitrogen and a carbon. That's what you can see at every single corner, right? So if you're asked to draw the repeating unit, you need to draw something like this. A carboxylic double bonded CO bonded with a nitrogen with one hydrogen, is bonded to its own carbon chain and nitrogen with the hydrogen. Then from this side, we have the carbon chain of the carboxylic. This is what the repeating unit looks like. And if you are asked to draw the polymer, then you have to draw a few linkages together like this, or draw the repeating unit and put a simple N. So even for the condensation polymerization that forms a polyamide with an amide linkage, there are two monomers that we start. Now let's have a look at the differences between the addition and condensation polymerization. Addition polymerization involves the removal of a carbon-carbon double bond. Ethene, some sort of a double bond, breaks to become a single bond and opens its arm to other such monomers so that they can become the polymer. So this means we only need one more monomer for the additional polymerization. But for condensation polymerization, it has two different monomers. It needs more than one monomer to undergo condensation polymerization. It also involves the reaction of two different functional groups from one long molecule by the removal of a small molecule such as water. So, unlike additional polymerization that doesn't remove any molecule, condensation polymerization will remove a small molecule like water. And the monomers also have to have the respective functional groups at both ends of the molecule. Otherwise, it won't work. Now let's look at some of the applications of synthetic polymers in plastics. Plastic polymers are polyethylene and PVC, polyvinyl chloride. These are the most widely used types of plastics or plastic polymers we know. Mainly, polyethylene and PVC are used for packaging purposes. Usually, these synthetic or man-made polymers are made in a factory. And from polyethylene to PVC to nylon, terylene, lycra, all of these are made by humans. Nylon is a polyamide, and nylon is usually used in clothing, fabrics, nets, and ropes. Terylene is a polyester. Polyesters are made by condensation polymerization with an ester bond. And this is usually used in the textile industry as well. Usually we use terylene to mix with cotton and produce cotton blends that we use to make different types of clothes. The problem with man-made polymers are that they are not biodegradable. Now, these plastics, they don't break down naturally. Just like how the synthetic polymers don't make themselves naturally, they don't decompose or break down naturally as well. Even if it does, it is very slow. And it takes hundreds and sometimes thousands of years to properly degrade. So plastics have now become a very serious pollution issue. There's a lot of marine life under threat and a lot of animals under threat because of the dumping of plastic. Oh, these waste polymers take up valuable space because most of the plastic either it goes into the ocean or it goes into landfills. And usually, how does any waste material get broken down? By microorganisms. Microorganisms can break down organic compounds and put it back to the soil. But the problem with plastics is that microorganisms, they can't break plastics down. So this is why they are not biodegradable. So if you dump plastics in landfills, they just pile up. They just don't disappear. The other alternative that most people do is burn them. If you burn polymer, they emit a lot of harmful gases as well as a lot of heat, carbon dioxide and other greenhouse gases. And this is an even bigger problem because this accelerates climate change. So burning is also not a solution. If it's burned as an incomplete combustion, then carbon monoxide is formed. That is a poisonous gas. Carbon monoxide is poisonous to humans as well as animals because it lowers the blood's ability to carry oxygen. This is because carbon monoxide produces a very stable compound with hemoglobin, the thing in our blood that carries oxygen. If carbon dioxide goes and pairs up with hemoglobin, it won't remove the carbon monoxide. And because of that, there won't be space for oxygen to be carried around the body. So carbon monoxide can be very toxic. It's a toxic gas. Polymers, however, can be recycled. So that means we use the polymers that have already been used, we put it back in the factory, crush it, and use different parts. There are actually different types of recycling that we can do. But these recycling processes are very expensive, very energy intensive as well. So they are also not so sustainable. On the same topic of recycling of polymers, synthetic polymers, there's a special type of polymer called PET. PET can be repolymerized. What does this mean? PET stands for polyethylene terephthalate. Now, this is a very common polymer that we use in plastic bottles. If you have seen most plastic bottles we use, they have the recycle symbol. If you dispose plastic bottles correctly, it can be repolymerized. Now, PET is a type of polyester that consists of repeating ester units. Even though recycling can be quite challenging, since it's very hard to uh, degrade the monomers, it usually takes very high temperatures and pressures to break down the polymers into monomers. PET can be easily converted back into monomers through depolymerization. We use enzymes or chemical methods to depolymerize PET. Instead of just using heat, we use the enzymes and chemical methods. Enzymes in microbes can break down PET into their original monomers. And solvents, catalysts, and mild heating can also achieve this same depolymerization. So either you can use enzymes or you can use certain solvents, catalysts, and a bit of heating. Not like any other type of depolymerization. PET can be done at mild conditions of heating. And then these recovered monomers can be used again to make PET polymers, new bottles, without creating waste. This reduces waste and also reuses resources. So PET is one of the most sustainable synthetic polymers out there. It has a less carbon footprint and it produces less garbage problem for the environment. Finally, let's look at one of the most common natural polymers, proteins. Proteins are also made out of condensation polymerization out of amino acid monomers. So the monomer for protein is amino acids. It is linked by amide bonds, or we call it peptide bonds, very similar to nylon. Now, remember, nylon is a synthetic polymer, it's not natural. But the linkage between nylon and protein, they're both amide or peptide bonds. So they're very similar. Amino acids are the monomers of protein, which has the NH2 and this carboxylic functional group. This diagram here shows an amide group. It has an amine group as well as this carboxylic sort of. Now, there are 20 common amino acids distinguished by their unique side chains. Side chain R represents different types of or different number of carbons and hydrogens that can be. It could be CH2, it could be C2H3, H4. So it depends. This R can represent any amount of carbons and hydrogens. And depending on this number of carbons and hydrogens, they have identified 20 common amino acids. And proteins can have 60 to 600 amino acids arranged in different orders. So there are different types of proteins depending on this arrangement and different types of amino acids used. And proteins is one of the most commonly found natural polymers everywhere in our hair, in our body tissues. Proteins are very common natural polymers. Now that we have covered the theory for this topic, let's have a look at a few past paper questions. Given above is a structure for chlorofluorocarbon polymer. What is the monomer used here? All right. Before we find the monomer, we need to first find the repeating unit. So let's look here. There's a carbon with a CH3 and a hydrogen. Then again, chlorine and a fluorine. Again, CH3 and a hydrogen. So already starting from here, it's repeating. The repeating units, therefore, for this polymer would look like this. H, F with two hands extending to either side. This is the repeating unit. And looking at the polymer and the repeating unit, you can say, because in the polymer, the bonds are carbon-carbon, just regular carbon-carbon bonds, the monomer should have been a molecule with a carbon-carbon double bond. So instead of these two extending hands to either sides, the monomer has to look like this. Carbon-carbon double bond with the same arrangement of molecules. of atoms. Now all we have to do is match this molecule with the given answers. So the condition is the carbon with CH3 must be bonded with hydrogen. The carbon with chlorine must be bonded on the other side with fluorine. Okay, so that's the condition we are looking at. Let's look at answer 1. Carbon here, the first carbon is bonded with CH3 and hydrogen. Okay, that's correct, CH3 and hydrogen. And the second one has chlorine and fluorine. I think we already have a winner. This is the correct answer. It seems to be the correct answer. You might wonder, but CH3 is not on the top. It is not on the bottom. That's okay. It's okay as long as they are bonded to the same carbon. Here, chlorine and fluorine are bonded to the same carbon. So this is consistent. But if you look at all the other 3 answers given here, they have a different pattern. CH3 and fluorine are bonded onto the same one. That's wrong. Here, CH3 and chlorine are bonded to the same carbon. So wrong. And here again, CH3 and chlorine are bonded to the same carbon. So 2, 3, and 4 are talking about completely different monomers. The correct answer here should be answer number 1. Now let's look at one final question. Which polymers occur naturally? Look at all 4 options. Starch and nylon. Out of starch, yes, starch and nylon, starch is definitively natural. But nylon is synthetic. Proteins in nylon. Again, nylon is synthetic. But proteins, yes, proteins are natural. Proteins in PVC. We know proteins are natural, but the problem is PVC is synthetic. Starch and cellulose. Both starch and cellulose are natural polymers. So the correct answer for this question is answer 4, starch and cellulose. With this, we have come to the end of the discussion of this topic. Thank you for listening.